So hi, I'm Joe. As Paul said, I'm at the University of Exeter. So I'm going to talk to you about the compost bomb, and this is work I've done with Paul, Chris Huntingford, and also Peter Cox. So this talk comes with a bit of a health warning. So the compost bomb is a theoretical tipping point. So there's going to be some speculation to begin with when we describe the mechanism. In the middle of the talk, when we're thinking about the maths, that's on much firmer ground, but we sort of dive off the deep end towards the end of the talk. So what is the compost bomb? So it's a tipping point in the soils caused by respiration. So the idea is respiration in the soils releases heat, which heats up the soil, which in turn increases the rate of respiration, which leads to more heating. And so you can get a sort of a runaway effect. So if we be a bit more mathematical here, to consider the rate of change of temperature as being due to A, so that's the heat of respiration, CS, the soil carbon, so that's the fuel, and then we normally model respiration with this exponential dependence. So in the absence of respiration, we'd expect the soil to relax to the air temperature, like so. But it's also the case that respiration uses up the soil carbon. So we should have this equation as well, and then we'll add carbon to the soil through NPP. So this model was first produced by Kat Luke and Peter Cox in 2010, and they discovered some interesting rate-dependent behavior. So if you rapidly increase the air temperature, the soil carbon doesn't have time to respond, and you get the thermal runaway. If you increase the air temperature slowly, the soil carbon can respond and decrease, which decreases the respiration term, so you avoid the runaway effect. So this is a figure illustrating this. So for 3 different rates of warming, you get 3 different soil responses. So this is a box model, and I'd like to make it more realistic by considering the vertical structure of the soil. So the first thing to do is to move this air temperature to a boundary condition and introduce diffusion of heat in the soil. So we've now got this parameter kappa, which is the soil conductivity. And you might also worry about the distribution of carbon in the soil. So we'll let it fall off exponentially with some scale height h. And then we've made 2 things more complicated. So we should make one thing easier and set the soil carbon to be in equilibrium. So now that the soil carbon is in equilibrium, we don't expect sort of this rate dependent behavior. We expect a more standard bifurcation. And I think conventional wisdom sort of suggests that this setup should be more stable than the box model because diffusion should sort of spread the heat out. But I think it's more complicated than that because when you go to the box model, you average these quantities, but averaging and exponentials don't commute. So to show you what I mean by that, so I consider this artificial example where we have a depth profile of temperature, which I plot here in red. And then I also plot on the average temperature. This is the temperature seen by the box model. And then I then calculate the respiration due to this average temperature in this black bar in some arbitrary units. And then I also calculate the respiration as a function of depth. And then I take an average and I plot that in this red bar. So by taking into account the vertical structure of the soils, we've ended up with a larger respiration, which might actually make the continuum model more unstable than the box model. So I think mathematicians might recognize this as a consequence of the arithmetic geometric mean inequality. So I take the continuum model and I just look to see if it's unstable numerically. So I raise the air temperature sinusoidally, so it reaches a maximum at 3 months, and then I bring the air temperature back down. But you'll notice that at 5 months, the instability is being triggered, and we get this thermal runaway. So now that we've got evidence of the instability, we ought to be a bit more systematic and look for the threshold as a function of a parameter. So here I choose the soil conductivity. So there's two important things here. So at large kappa, when the temperature should be well mixed and the vertical structure matters less, the continuum and the box model agree. So the box model is this dashed line. But for lower and probably more realistic values of kappa, the continuum model is much more unstable. So that's the numerical stuff. But there's also analytic results. So I take the continuum model and I non-dimensionalize it. So theta, tau, and x are non-dimensional temperatures, times, and space variables, which lead to these parameter clusters, W, which represents respiration strength, and D, which is a sort of a thermal scale height. And you can solve this for the steady state. And when you do that, you end up with this integration constant, C2, which you fit from boundary conditions. And it turns out you can only do that if you have a sufficiently low air temperature. So that's just, I suppose, analytic proof of a compost bomb in this model. So one of the ways you could cross this threshold is through a dangerously large seasonal cycle. So I numerically work out how large a seasonal cycle in temperature would have to be to trigger a compost bomb as a function of kappa. So again, I think there's two things to say here. So the first thing is the amplitude of the seasonal cycle you need to cause a compost bomb is always larger than this threshold warming, which I plot in the black line and the red lines. And this is an example of overshoot, which I think Paul is going to talk more about later. And then the other thing to say is that at low and I think realistic values of kappa, we see that this amplitude is something like 30 degrees. So this is a large seasonal cycle, but in certain parts of the world, it's realistic. So I worked out the amplitude of the seasonal cycle for 2020, and I'm looking somewhere over Siberia. And you'll notice that in this sort of top right region of these high latitude regions, you're getting seasonal cycles of about 30 degrees. And if you've been following the news this summer, you might have noticed that Siberia had a very nasty fire season this year. And a lot of the nasty fires were concentrated around here. And part of the reason the season was so nasty because of these things called zombie fires. So they're also called holdover fires. So the idea here is that, say in 2019, you have a fire caused by lightning or whatever. This then burns through to the subsurface and can sit there smoldering in the peat over winter. And then when it does this, it can then next summer re-emerge like a sort of a zombie rising from the dead. So you get a fire almost from nowhere. So what I want to cautiously suggest is that maybe some of these zombie fires are in fact compost bombs, in that they're fires that seem to emerge from nowhere. But I think that's one thing that needs some further research. So to summarize, the compost bomb, which is a thermal instability in the soils, it exists in simple box models, but it also still exists when you take into account the vertical structure of these soils. If you extend to, and in extending to this vertical structure, in fact, makes the soils less, not more stable. And then the sort of the final speculative thing to say is that we might have already seen some of these compost bombs, and we need to look into this further. Thank you.